Thank you for attending today's webinar. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple application widgets you can use. All the widgets are resizable and movable. If you have any questions during Redcast, you can submit them through the Q&A widget. Please know we do capture all questions. Check out the resource list for helpful resources and links. Submit your question using the Q&A. Okay, some helpful tips for the webinar. Records are streamed through your computer so there is no dial-in. Make sure your computer speakers or headphones are turned on and the volume is set to an audible level. Webinars are also bandwidth intensive, so closing any unnecessary browser tabs will help conserve your bandwidth and issues. Hardwired internet connection is recommended. If you're not seeing the slide advance, please press refresh by pressing F5 or Command+R for Macintosh. For a certificate of attendance, go to learn.bentley.com or directly access to learn.bentley.com/transcript. If you don't have a profile yet, go to ims.bentley.com to create one. Now I will pass on to William to start off with the presentation.
Good morning. Welcome to a webinar on modeling of excavations and influence on groundwater. An introduction. In this webinar, we have combined two major subject matter, modeling of excavations and groundwater. In a normal course setting, these two topics would have taken at least 3 hours to complete and cover. Therefore, we have made some simplifications, kept the important parts which we think will be suitable as an introductory note and guide. Part 1, the presentation outline. This presentation and webinar is divided into 4 parts with 3 major parts, Part 2, Part 3, and Part 4. Let's have a look at Bentley Geotechnical Engineering. Praxis 2D, 3D, and Praxis Modeto is part and forms the core of geotechnical analysis. Before I move to part 2, I would like to bring your attention to the resource list. On the list, there are 5 links. You will find the link to the documents for Praxis 2D and 3D CE, link to Praxis software, and link to the Year in Infrastructure 2019 Advancements in Geotechnical Engineering in the list as well. There's a related video available on demand, which is concerned with the modeling of excavations, dewatering, and some common pitfalls.
Before moving to part 2 of presentation, we have a poll question, which you can see on your screen, and you have 10 seconds to respond.
Part 2, Excavation. The outline of Part 2. We will first look at some of the key aspects of excavation, the creation of the finite element model, the boundaries, idealization, discretization, when do you do a 2D or when should you proceed with a 3D, and we will look at the structural elements and the soil models. This part is a very short section. The idea is to introduce to members of the audience some of these key features that you need to consider when you undertake geotechnical finite element analysis 2D, 3D. Numerical analysis of deep excavation. A involves modeling of multiple excavation stages. Soil structure interaction, war-soil, interface elements are important. You need to consider the changes in the groundwater level at the beginning, at the end, and during the analysis. Struts and anchors, load transfer to soil, and you need to consider as well the influence of adjacent structures, whether it is buildings, tunnels, or foundations. It requires advanced constitutive model because stress paths in soil are not monotonic. You'll see in part 4 one example and the importance of using an advanced model when predicting deformation and failure. Primary loading and loading occurs in different zones of the domain of analysis. Some areas will be in very small strain range, and some will experience large strains with significant plastic deformation. Simple, elastic, perfect plastic models are not sufficient, and you shall see why in the coming slides. The workflow in Plaxis 2D and 3D. For those of you who have been using Plaxis for some time, these by now would have been a very common sight. And for those of you who have just joined us or about to embark in the use of Plaxis to perform the technical finite element work, there are 5 important modes in Plaxis 2D and 3D. Mode 1 is concerned with the soil. Mode 2, structures. Mode 3, mesh. Mode 4, flow conditions or water conditions. And mode 5, the simulation, or what we call the stage construction, where you create the various phases of simulation. Mode 1 and 2 is where you create the geometry, beginning with the construction of the ground model using soil layers. Thereafter, in mode 2, the structures mode, you create all the entities and the items and the components that you need to model the geotechnical or structural geometries, loadings, using the 2 sets made available in these 2 modes. Mode 3 is concerned with meshing, or in FEM, discretization. It is where you refine and optimize the arrangement of mesh in the areas that are of concern. Mode 4 is water conditioning, and mode 5 is the creation of simulation stages and calculation types. Many geotechnical problems are 3-dimensional in nature and require some degree of idealization and assumption to 2-dimensional plane strain or asymmetry to render them soluble within realistic turnaround time on existing computer platforms. We need to consider carefully what is the effect of such idealizations, assumption made on the solutions. For beginners, the 2 tables seen on the screen will be a good introduction and a guide on what you need to look for, concerned with when modeling 2D or 3D retaining systems. Geometry and idealization, 2D, 3D. Whether to build the FE analysis model in 3-dimension or 2-dimension is one of the most challenging questions. Conduct 2D analysis when possible to save time and resources, but only when the idealization and assumption made are correct. Setting up the geometry for a typical 2D analysis of a section may take about a day, for instance, while to set up a 3D full model of the same structure may take a whole week. Using a geometrical assumption, whether plane strain or symmetry, is an important decision because there can be enormous difference in the workload between a 3D model and a 2D plane strain or asymmetric. 2D asymmetric assumption. A 2D asymmetric model also involves analysis of a plane and vertical section of a site, except that one of the side, a vertical side, in plexus on the left hand is the axis of rotation of symmetry. This assumption and idealization is suited to problems with a vertical structure in the ground with a constant uniform radial cross-section, for example, a shaft or circular cofferdam. Nearby features needs to be considered: loading, local or non-local, symmetrical or non-symmetrical. 2D plane strain assumption. This assumption and idealization is suited for geotechnical problems where a uniform cross-section, including the ground layers and the surface, the state of loading is constant along the outer plane or long direction. A 2D plane strain model involves analysis of a plane and vertical section of the site. The strain and displacement in the third dimension, perpendicular to the plane, is assumed to be zero, and hence the strains will occur within the plane and they are independent of the outer plane direction or the in-screen direction. How detailed does the geometry need to be? In the current advancement and with geotechnical engineering moving towards beam and digital twin adaptation, the level of detail, also known as LOD, is very important. How detailed does the geometry need to be? That is the question. To save time in setting up and running analysis, the geometry of the FE model needs to be as simple as possible, but not by compromising the accuracy. As with many decisions to be taken when setting up a geotechnical finite element model in Plexus 2D and 3D, it comes down to a compromise between the level of detail and efficiency and the turnaround time. Use enough detail to obtain correct, accurate key outputs, but not excessive to the point that it blows out the analysis. This will be time-consuming and expensive. These decisions has to be made using judgment, experience, and training. If in doubt, perform tests and validation runs. The geotechnical industry will be embracing digital twin very soon. Interoperability and integration with structural, civil, and architectural, and in fact, even reality modeling solutions will be very important in the coming decade. Here, let me demonstrate some ideas of a plane strain analysis or plane strain model and a 3D unit slice. On one end, you can see that the analysis can be done in a 3D unit slice, but because of the nature of the geometry, and the loading condition, the 2D plane strain analysis can perform as well as a 3D unit slice. So this slide shows you the different flavors of a modeling scheme, 2D plane strain and 3D unit slice. But it also teaches us that, when you have a model which can be modeled as a 2D plane strain, you should do so. Some other models for plane strain, on the left-hand side, 2D model could be sufficient. And on the right, a typical 2D station box excavation using Plaxis 2D CE. And on the screen, you can see the usage of asymmetry and 3D half models. Again, first and foremost, to demonstrate what we can do with Plaxis 2D and 3D, the type of models. But if you look at it on the 3D half model, the soil layers are horizontal, the loads are constant throughout the plane, and in fact, this could be better model in terms of time and efficiency using plane strain, using asymmetric 2D modeling. And on the charts on the right-hand side, you can see the response coming from the asymmetric analysis and the 3D half model analysis. These are quarter and half models. There are times it is not necessary to create a full 3D model. When you can find symmetry and you can find that the assumptions are right, you can create and construct these type of models. This is a 3D full models. There'll be a situation where a complete 3D full models are needed in analysis. Level of detail, as I mentioned much earlier before, to save time in setting up and running analysis, the geometry or FE model needs to be as simple as possible without compromising too much on accuracy. As with many of the decisions to be taken when setting up a geotechnical FE models comes down to a compromise between detail and efficiency. Enough detail is required in order to obtain reasonably accurate key outputs, but not excessive detail such that the task becomes unnecessarily time-consuming and expensive. Adding more, with the connected digital environment, interoperability, and digital twin, the future of geotechnical finite element modeling analysis is going digital, integration, and interoperability. The basis of LOD system is that the numbers describe the different levels of detail and development. So in this analysis, an LOD 200 and 300 will be a good start. Not too simple and not too detailed to the point of increasing the creation of the model and calculation time. Model boundaries. This is a very important factor when you create FEM models. Where should we place the boundaries? The fixities are applied at the boundaries to the model, but in field situation, there is often no obvious boundary for the FE model because the ground extends indefinitely. The boundary should not be placed too close to the area of concern because that would be unrealistic and would cause boundary effects. The only common situation in the field where the boundary could correctly impose a significant condition is where you have a soil overlying a rock material, and that interface will then form the bottom boundary. The FE mesh needs to be fixed in space in order to establish equilibrium and solve the global stiffness equation to determine displacement. Hence, refinement, and organization of mesh will be important. Discretization. What makes a good mesh? The size and arrangement of elements in a mesh can have a critical effect on the accuracy of an FE analysis. A poorly formed mesh will cause a lot of problems and errors. Large stress concentrations and zones of rapid stress, including pore pressures of strain, need smaller elements to allow better representation and calculation. A mesh form of higher order elements can be of coarser because of the higher number of nodes per element. Note that the prediction of instability or collapse is heavily influenced by mesh geometry and element type. Distortion is less of a problem for triangular and tetrahedral elements, provided that the sides of each of these elements are of the same length. A good FEM mesh is graded with small elements in the area of concern and when they are needed, and it connects to the boundary, and at the boundaries the elements can be larger. These will allow faster computation times without significant loss of accuracy. To check whether the mesh is adversely affecting the output, try running analysis with finer mesh and check that the key outputs, they don't vary too much. In this section, we will talk about structural elements. I'll provide some key summary, and it is not a comprehensive presentation. I'll be giving you some resources whereby you will find video links and also papers and also resources where you can learn a bit more on structural elements. In Plaxis, the structural elements needed to model structural entities, the plate elements, the anchor elements, the tactile elements, interface elements, embedded beam row elements. Please refer to the Plaxis manual for further information, course notes, and on-demand videos made available by the Plaxis team. Some typical examples of what you can do with the structural elements, used solely or in combination. In the modeling of excavation, there's always a question of whether to model the wall as a plate or using a continuum. So this is the thick wall versus the thick wall question. For thin wall is where the wall thickness is very, very small as compared to the wall length, and no end bearing and only friction is of interest. So the plate element will be the correct usage. For thick element or thick wall, the wall is a significant thickness and end bearing is needed as part of the soil structure interaction analysis. In this scenario, you should use the soil elements or the continuum approach with a material set representing the wall material. In order to obtain structural forces, a plate is sometimes used with fictitious properties. This is known as the paper plate or the dummy plate approach. With the current release of Plaxis CE, you can use the integrator tool to obtain the forces along the volume elements. Thick wall approach. You can use this approach to model thick walls. Wall support. Some details that you might want to include. The lagging. using short additional section of a plate perpendicular to the wall. Create a short section with increased stiffness. Struts could be node to node for full excavation. And half, you can use the node to fixed end. For anchors, which are predominantly spring elements, it can be used entirely on its own as a strut, or it can be combined with, in this case, the embedded beam roll in 2D or embedded beam in 3D to form grouted anchors. Some important points to consider when performing analysis using ground anchors. Ensure that you have sufficient elements to create good output of the shear force transfer. Comparing to textile, embedded beam roll is a much better structural element to use in combination with the node-to-node when modeling ground anchors. Some practical usage of the input box and plexus for an embedded beam roll to model the grouted zones. For the modeling of excavation, it's predominantly a soil structure interaction problem. So the interface elements they're needed to provide a stick and slip relationship. The interface elements handle normal and shear behavior. And the soil properties can be taken from the adjacent soil through the usage of I-inter, you wish to do that. Or you can also create a separate material sets and place it along the interface. Additional features of the latest releases of the interface elements, you have the ability to model gap closure and also the residual strength when you reach a maximum shear strength. Soil models, a quick summary. The standard models and the UDSM models. The standard models, going from the top in its simplicity, is linear elastic model, and all the way to the bottom, you have the concrete model. UDSM, user-defined soil model. During the modeling of deep excavation or excavation, the excavation is entirely of unloading in nature. You have the vertical unloading in excavation bottom and the horizontal unloading behind the wall. And you have also the primary loading caused by, for example, in this case, the preloading of the ground anchor. And you can see that on the screen, the stress path, pictured here using the sigma V, sigma H plot, how, say, the point A and point P shifts from the K0 position. This is a very important point to recognize because to enable you to perform, conduct, and create good geotechnical FEM models, you could ensure that your soil models are able to capture these sort of things. In a nutshell, a more column model, unrealistic for deformation, tends to overestimate the bottom heave, often heave the soil behind the wall, and it can stretch as far back as 10 times the excavation height. The hardening soil model qualitatively is realistic in the capture of deformation, better bottom heave, but increases with model depth. Sediment trough behind the wall is good, but often too shallow and too wide. The HS small model, qualitatively and quantitatively realistic. Good bottom heave prediction independent of model depth, and more realistic sediment trough behind the wall. And on the right, you can see the domain of the excavation problem. And various zones basically react at different stress path, strain level, and stress level. And hence, the operating soil modelers can vary. One of the other features of Plexus 2D and 3D CE is the availability of the soil tests. It is a very important module. It allows us to calibrate the soil respectively to the laboratory measurement, whether through the triaxial stress path, odometer, 1D confined compression, and a host of other tabs that allows you to capture all sorts of calibration. It also has these parameter optimization. Once you have done the first set where you able to map up the parameters, you may want to use the optimization tool to calibrate certain features, say for example the HS model, whether the problem is of a volume in nature or of a shear problem. You can use the optimization tool to match the response at various stress, strain, and stress path. Hi, ladies and gentlemen. Before we move on to the next section, we have another 10 seconds for the second poll. So please feel free to answer the poll. Thank you so much. Part 3, groundwater. Outline of presentation. We will look at the different pressure terms, pore pressure terms in Plexus. And we will look at how the background steady state or at rest pore pressure can be generated. We will look at semi-coupling and full coupling and some examples. And we will look at when should you consider a short-term, long-term analysis. Pore pressure terms, useful to divide the pore pressure into different terms because there are different options for the way each is calculated. In Plexus, you have the steady state pore water pressure. This is akin to the background at rest pore water pressure. Excess pore water pressure is a non-equilibrium pore water pressure. Active pore water pressure, also known as the total pore water. Steady state. This is address or background pore pressure arising from constant hydraulic boundary conditions, purge, static, or constant extraction rate from a well. This part of the pore pressure does not change with time during analysis. It is possible to change the boundaries, hydraulic boundaries condition in an analysis phase manually. For example, in mode 4, at water condition to establish a new SS background pore water pressure. Excess. This is the change in pore pressure from a steady state value caused by loading, unloading, or rapid change in the hydraulic boundary conditions in undrained or consolidation conditions. Excess pore water pressures are calculated by the FE kernel and is also influenced by the soil model that you use. Active, also known as the total pore water pressure in a real sense, is the actual value of the pore pressure, the sum of the steady state plus the excess. Steady state pore water pressure can be generated by either assuming hydrostatic condition using the phreatic line input, global or cluster approach, or the steady state background pore water pressure can be generated through the use of a groundwater flow, steady state. It's a pore pressure arising from a constant hydraulic boundary conditions. Pore pressure does not change with time during displacement or conservation analysis. It is possible to respecify the hydraulic boundary conditions in any analysis stage. In this case, at each phase, you can go to the water condition mode to change the hydraulic boundaries. This pore pressure can be specified directly for horizontal phreatic surfaces when setting up the initial stresses or in subsequent analysis stages. Excess pore water pressure, change in pore pressure from steady state value caused by loading, unloading, or rapid change in hydraulic boundary conditions in undrained and consolidation conditions. It is dependent on the constituted model. It's relevant for plastic analysis, AB, and consolidation analysis. This chart shows you the relationship between the steady state background pore water pressure and the kernel where the excess pore pressure are generated. On the left, you can control the background by the usage of hydraulic boundary conditions at one phase or another. But for the P excess, this is controlled by the FEM kernel and as well as the usage of various constitutive soil models. From the bottom up, or from the top to bottom, where you have that simulation stages, you can see that the pattern of change in the steady state and on excess, and as a result of that, you get the P active, which is also known as the total pore water pressure. Pore pressures, how do you generate P steady? You can do so by either through the use of the phreatic or the water lines, or through the use of the groundwater flow calculation kernel. Water levels can be of a global water level, which by default is based on the position of the water level that you input in the borehole box. And you can also change it in the soil mode and water mode. Bear in mind that you can also create additional water lines known as user water line. 1, 2, 3, 4 is possible. Now, the steady state pore pressure generation, as I said earlier, can be based on the global water level. It can be customized, known as a user local water level input. it can also be created, adjusted, based on the cluster drying approach using your right mouse button gesture. And you can also interpolate between clusters. For example, here's one. You first create the position of the water level based on the position of the water. So you have cluster 1, 2, 3. And from here, in the flow conditions or water condition mode, you can assign a cluster to that global level or through the user water level. For example, this is the default setting when modeling using only one water line on the left. But on the right, you have the global, which you input from the borehole, but you can also create additional water lines in the water mode to create different pore water pressure subsets. Another thing that we need to explain is that you have a sheet pile wall which is floated in the soil, and if I can put it simply, it is just one single swimming pool. The pressure at the back and the front of the toe should be the same. The way to model this to the drop of water table is not to the use of a change in this step line, or known commonly as the Z-line approach, because if you look at the results, the pore water pressure generated from this approach is that anything beneath the toe, you can see a jump of the hydrostatic pore pressure. This is incorrect for a situation where the toe of the excavation is not socketed in the impermeable layer. To do it, this is the way to go as an alternative to method Z, is to use the local water line in conjunction with the global water line. And you can see the brown zone is in fact the interpolation zone, and the zone marked in red is being referenced to that local line, and the remaining clusters are being referred to the global line. With this, you generate a pore pressure which is physically correct for a problem where the actuation toe is not socketed into the impermeable layer. Performing groundwater flow, as I said, steady state can be generated through the hydrostatic approach or by a steady state groundwater flow. Calculation is based on or takes into account of the boundary conditions. The boundaries right now could be closed or opened. Other inputs or valves and drains can be used. The interface elements right now is useful. If it's on and active, it is impermeable, and off is permeable. And in fact, in the latest releases, you can also have partially impermeable and permeable. Soil permeability right now is important. The phreatic line of soil is calculated based on the time infinite, and the still defined phreatic levels can be used to create or set up the initial position of the hydraulic boundaries around the model. Here's a case, for example. You have the phreatic line being sloped to the point, but that doesn't mean that the water positioned or the pore pressures will be generated based on the slope of the ground. What is important is that the position of the water touching the exposed or at the base of the excavation and by the side, it actually creates the correct piezometric head inputs for the groundwater flow steady state to calculate the pore water pressure. Hydromechanical coupling can be semi-coupled. The semi-coupled is a steady state pore pressure defined in the first instance, and followed by a stress analysis with possible excess pore pressure generation on drain A or B. The active pore pressure then is the combination of the steady state and excess pore pressure. Now, for a full couple analysis, This can only be done with the transient calculation module. And when this happens, only the total pore water pressure is being considered, which means the P steady and P excess will no longer be calculated. Everything's resolved to the total water pressure. Where do we fit all these things in? Initial hydrostatic, steady state at the far end, with time is infinite. In between is where the transient pore water pressure is relevant. For example, we begin analysis of a ground whereby there's no water flow. The water is perching or standing. To the passage of time, if you allow the water to flow, it will reach a steady state. And in between t time of 0 and t infinite, you have time at t1 and t2. This is all transient flow. Let's look at the first example of groundwater around a retaining wall or an excavation. If the groundwater table is high behind the wall, a substantial amount of the total stress will be contributed by the pore water pressure. For example, let's look at a strutted excavation whereby the toe is founded in drained soil. The water control, toe conditioned, soil type, duration, and water or wall water tightness. You can see on the plot of the graph on the right hand side, the pore water pressure contributes a lot to the total pore pressure acting on the active and also on the passive side. Let's look at case 1. Wall toe socketed into the rock, perfect water cutoff. Now this is a two swimming pool problem, so to speak. The pore pressure on the left, or the water pressure on the left and the right, they're separated by that impermeability cutoff. And the water pressures on the wall should be something like this. Not just really a balance between the back and the front pore pressures. Case 2. Wall toe founded in permeable soil. Now instead of a separation of the two sides, the two swimming pools on the front and the back, you have one single pool and the toe is not locked into the impermeable layer. So you can find a flow coming from the back to the front. For such problem, for a material that is permeable, you can use the steady state groundwater flow option to get a good handle on the what could be the pore water pressure as a start and during the analysis. From case 2, this is generated pore water pressure contour, and on the right is the water pressure diagram in the back and the front. 3b. Let's look at the condition whereby you have layers of different permeabilities, the alluvium, the fill, and you have clay in the middle. The clay acts some sort of like a barrier between the fill and the alluvium. And you can see the water recharge comes in from that zone on the left hand side. Case 4. This case is real. Different water conditions on both sides. One is higher, one is lock-in the impermeable material on the right hand side. But on the left hand side, it's floated. And you can conduct groundwater flow analysis to get an idea what sort of the pore water pressures around the excavation pit. And this is the generated water pressure contours for case 4. For example, in excavation near seawall, look at the complexity of the layers, the alluviums, the clays, the CDG, and the fills. And you have on the right hand side, sheet power wall and the grouted zone. These all can be modeled. So this is generated pore water pressure based on that hydraulic boundary and permeability setup. Next is to show some other interesting conditions around excavation. Let's first compare the groundwater lowering between a steady state and a transient groundwater flow calculation. On this slide, you can see a three-stage excavation of 5, 10, and 50 meters, where the permeability is constant. For a given permeability value, a steady state, groundwater table drawdown is nearly proportional to the excavation depth. For this condition, fixed geometry configuration but variation in permeability, you have three pictures showing an excavated depth of 15 meters, but in each of these, the coefficient of permeability is varied from 1 minus E5 to E7 and to E9. And for SSKs, the steady state case, the groundwater table is not dependent on the K. Pattern of groundwater head is a function of geometry only and soil layer arrangement. Let's look at the groundwater table and transient seepage analysis. For this problem, a given excavation depth and comparing sand and clay type of soils. For soils with a sand-like hydraulic behavior, very close to a steady state, conditioned. For clay soils, very little lowering and very close to the perch and static water table. Now let's look at the next instance, groundwater flow or groundwater table with transient seepage. We are looking at an excavation depth of 10 meters now. Same set of permeabilities, 1 minus E5, E7, E9. Again, the sand at 10 meter excavation is like SSKs, steady state, and the clays is very little lowering, a groundwater table. So let's look at the next thing. The question is, when do you perform a short-term or long-term analysis into technical engineering? In an drain analysis, the excess pore pressure is not allowed to dissipate, but in reality, consolidation and dissipation of excess pore pressure starts immediately on loading. It is sufficiently slow in some cases for undrained conditions to be reasonably assumed for field problems. Undrained condition does exist too when the rate of loading is relatively higher than the soil permeability, which occurs in most construction, in clays, in low permeable ground. Drain means that the water is free to flow through the voids of the soil, hence no excess pore pressure are developed. Loading rate is low in relation to soil's coefficient permeability, and this most often occurs in the type of problem where you find in sands or gravels. Modeling drain condition is very straightforward. Modeling of undrained conditions in stratigraphic analysis is a challenge. Short-term versus long-term behavior again. Two situations can be considered: short-term, long-term. In the short-term behavior, two possible modeling strategies: total stress approach, which is undrained C in plexus, or the effective stress approach, or approaches using method A and B, whether you want to see the correct pressure development or the type of constitutive models that have been used. Between these two conditions of short-term, long-term, drain, undrain, consolidation and time-related analysis can be considered. With Plexus CE, you can perform test runs to check whether your analysis should be performed entirely under short-term, undrain, or long-term, drain, by performing quick test runs, test checks, consolidation calculations. Once this is ascertained, plastic calculation type with undrain and drain can then be carried out. However, as you can see on the slide here, in many geotechnical boundary value problems, the real in situ condition can be transient and time dependent. If that's the case, it is best to run a full couple analysis or consolidation analysis to find out the correct answer. Well known amongst Plexus Advanced users is a first check to see whether analysis should be done entirely or assumed to be of the short-term drain or long-term drain, is the use of the equation of Amir in 1998. This, as suggested by the equation for deep excavation, the equation here on the right-hand side, T is the dimensionless time factor, followed by the K times EUT divided by gamma W D squared times T. And on the chart on the left-hand side, the numbers would help you to decide whether your problem is closer to an undrained or drain condition. Undrained behavior with Plaxis, just to provide a summary on the type of undrained analysis that can be conducted in Plaxis CE, 2D and 3D. It's method A, method B, method C. In method A, the type of material behavior is undrained A, effective strength parameters, effective stiffness parameters. For method B, type of material behavior is undrained B, undrained shear strength, and effective stiffness parameters. For method C, the type of material behavior is undrained C switch, using total strength parameters and undrained stiffness parameters. These are all done using the plastic calculation type.
The third poll question is on your screen. Please respond to the poll question. You have 10 seconds to respond.
Part 4. Part 4 is concerned with the application examples. In this part, we will show 4 simple cases, and we will begin with the first one. The first one is concerned with the modeling of a sheet pile wall with 3 types of soil models: the linear elastic perfect plastic Moore-Coulomb model, the hardening soil model, and the hardening soil model with small strain. We will then compare the ground movements, the wall displacements, and wall stability. These are the parameters for the tree analysis using 3 different material models. The top table are the strength parameters for the analysis. You will see here that the Moore-Coulomb HS Moore model, the 3 of these models, they use the Coulomb-Filler criterion. Now, at the bottom will be the table where you can find the parameters for the EUT, E50, and E unload reload, the PREF of 100. For the Moore-Coulomb, because it's of a single stiffness model, you have only the so-called average E value. This slide shows you, in a simple sense, the difference or differences between the 3 models. On the top is a linear elastic perfect plastic model with the Moore-Coulomb-Filler criterion. The primary loading curve and loading reloading curve, they're on the same slope. In number 2, you see the hardening soil exhibiting the nonlinear and also the stress path dependent response, because the EUR, the slope of the EUR, is a few times larger than the E50. And on the right hand side, this is the shear modulus degradation curve. That means the shear modulus decreasing as an increase of shear strains. The results? More Coulomb predicts an unrealistic heave, 4 mm. HS small, first and foremost, predicting a settlement is a spandrel shape or settlement 9 mm. And at the excavated site, you see the more Coulomb predicts a heave of 20 mm, and the HS and HS small predicts 11 and 8 mm respectively. Predicted wall displacement. First of all, let's look at the response and trend. More Coulomb predicts a 6 mm movement at the top, and as well as some toe movement. For HS and HS small, although the total displacement is huge, but at the toe of the sheet power, you see the clamping effect. For the prediction of factor of safety, all three models predict the same factor of safety, and this is correct because all the three models they share the same failure criterion. In summary, more Coulomb predicts an incorrect surface heave behind retaining wall. But in terms of prediction of stability or instability, all three models provide the same factor of safety. It is important to recognize that when we are looking at pre-failure deformations, the soil stiffness is a very important point to consider. Soil stiffness is not constant and it varies with stress level, strain level, and stress path. And during excavation, soil elements at different locations of the domain experience different changes in stress, strain, and stress path direction, which you have seen in the earlier slides in part 1 and part 2. Let me show you a typical stress path near an excavation. This is from the GQ Note 1-90, and on this chart, showing the shear versus the mean stress for point A and point B. And now, look at the next slide. These are the stress paths that were predicted by Plexus using HS and HS small, and they look almost the same. It is important to recognize that the soil stiffness is stress path dependent, as shown by this chart. And another component to recognize is that the stress path dependent stiffness, for example, in the CDG. And here you also see the dependency of the shear modulus versus the shear strain. Why MC predicts incorrect surface heave behind wall? MC models a constant soil surface soil stiffness prior to failure. This is not realistic. In reality, stiffness of soil elements near excavation varies according to stress level, strain level, and direction of stress path. Realistic prediction of wall deflection and ground settlements in all excavation stages requires a constitutive model that considers the above factors, for example, HS and HS small. HS and HS small consider the interplay between factors 1, 2, 3 in determining the operation soil stiffness during analysis. E is changing during excavation. It's not constant. Example 2. Example 2 is concerned with Dragon Center. This is a 9-story RC building with 5-level basement. And the excavation pit has a planned area of 107 times 67 meters. And the excavation was conducted in a top-down manner with a depth of 27 meters. The wall has a thickness of 1.2 meters to rock head. Soil profile, fill, sandy marine deposits, completely decomposed granite, locally known as CDG, and also HDG, and bedrock. The groundwater is located at 1.5 meters below ground level, and in this analysis, we take into account of the various stages of construction: pumping test, groundwater recovery, and deep excavation. This is a well-documented case from 1994 with field measurements. Before we begin with analysis, because the prediction of deformation is of concern, and the idea is to use the HS more to make a good numerical prediction, we begin first by calibrating the nonlinear soil stiffness from very small strain for the CDG. And on this chart here, you can see that you have the triaxial data or the laboratory data. And at the small strain region, we don't have data. Using the HS small model, we're trying to fit what could be the upper, lower, and from there we adopted the baseline response for the analysis. The lower table shows the rest of the parameters, and for any of the users or numerical analysis who's keen to back analyze these case history, you have the data here in this video. The model is a 1/4 model, and the D-wall is modeled by a plate. And the same problem was modeled by Malone in 1997, but instead of using 3D, it was done in 2D using the brick model of Simpsons. On the left, you have the full geofence model, and on the right, you can see the slabs, the stanchions, and the bore piles. We will look at the response of these elements. So the first, let's look at the inclinometer, I3. Where is I3? I3 is on the shorter side of the wall, the center portion, and I6 is on the long side of the wall. So at pumping test, groundwater recovery, final excavation. The prediction made by HS small is reasonably good in terms of trend and magnitude. I6, again, it shows similar response. And for such problem, in this case, Dragon Center, the colony effects are one of the key things to investigate. And this picture here shows the way the corners are restraining the deformation. Of course, being exaggerated 120 times to get a look of how the wall sort of warped. In terms of ground surface settlement, you have the I3 and I6. Again, the HS prediction shows the correct, almost correct settlement profile. Few measurements seems to show is a bit more narrower. It could be other effects, building stiffness on top of it. But at this juncture in time, as a first set analysis, the HS model seems to be able to predict the response very well. Now let's look at the response of piles situated at the back of the wall along the long side. You have the 3D model on the left and the 2D model on the right. And we will look at the D-wall interaction or the pile interaction in the D-wall at a spacing of 3 meters, 7.5 and 50 meters. And for the case of 2D, the pile is modeled as a plate, and in fact, it is a wall. So comparing the pile deflection, 3D, 2D, for a spacing of 3 meters, 7.5 meters, and 15 meters away from the wall line. At 3 meters, 2D is located between the pile response of A, B, and C. And as the pile shifts back away from the long side, the response starts to get narrow in terms of the 4 predictions, A, B, C, and 2D. Pile bending moment, again, at a spacing of 3 meters, the response is very acute. Look at A, B, C, and the 2D prediction. Now for S, a spacing of 7.5 meters, 2D, or should I say, pile A, pile B is responding very closely to a 2D response. And as the pile steps back further away at 15 meters, all the piles A, B, C are responding in almost a 2D response. Let's look at the ball piles in the excavation pit. You have the 2D response, which is the black line. You have the pile response of X and Y. X is at the center, and Y is very close to the excavation pit. It can be seen that the 2D analysis using the wall plate approach predicts a very large tensile force. So summary, for the Dragon Center case, as lateral distance between pile and back of D-wall increases, 2D pile wall analysis underpredicts pile deflection by up to 50%. As pile gets closer to the back of D-wall, 2D pile wall analysis overpredicts pile bending moment by up to 40%. For piles located within the excavation pit, the 2D pile wall analysis predicts pile tensile forces up to 4 times larger than the 3D individual discrete analysis. 2D pile wall analysis cannot consider the wall corner effect, and hence you can see the results of in the chart of ABC, the different response. Again, in the 2D pile wall analysis, the piles modeled as plate does not allow the interaction of the front and the back soil, so it's being shielded. Also, when you model the pile as a wall, it provides too large a surface area at the interface, and hence it will attract high tensile forces. Above limitations can be slightly mitigated using the embedded beam in 2D, but then again, it is best to check with a proper 3D analysis. Example 3. First of all, I'd like to thank Professor Stryker for sharing these slides. They are part of the course notes for the deep excavation course that we conduct in Asia Pacific. In this 3D example, we will look at, again, a 3D problem, but it will be modeled as a quarter model. We're looking at the geometry of the quarter model in plan view. And this is the cross section of the excavation and retaining system. In this model, model dimensions x, y, z respectively, 50, 60, and 60 meters. Mesh is close to 150K tetrahedral elements. So what are we looking at? We are looking at a parametric analysis. In part, these example and modeling exercise is a continuation of works done by the Imperial College Group. So the modeling, we will look at isotropy, linear elastic material behavior, anisotropy, plate elements, linear elastic material behavior, continuum elements, jointed rock model to capture anisotropy, and those are assumptions as listed under the page in terms of the what are the Poisson's ratio and the E sub 1 and E sub 2. On the right, it shows the directions of E1, E2, N1, N2, N sub 11, kappa sub 11, M sub 22, and kappa sub 22. So the calculations performed, isotropic plate elements were modeled with rigid and ringe connection. Also modeled with volume elements. For anisotropy, plate elements with rigid connection and also with volume elements. We've also looked at undrained analysis, a coupled analysis, a consolidation analysis, and a drain analysis. So this will give you further explanation and ideas from where we stop from the groundwater part 3. So looking at drainage conditions, if you look at the trend, the horizontal wall displacements, the red line is for the drain response, isotrophic, and the black line is undrained, isotrophic. And you have the coupled 1, coupled 2, and consolidation falling in between the bracket. And in terms of the prediction of maximum horizontal wall displacement, the drain analysis predicts a relative difference of 62%, and the rest, as you can see, 58, 38, and 47, reading from drain to the undrained direction. So this being compared to the undrained value. Now on the bending moments, again, comparing the 5 conditions: undrained, coupled 1, coupled 2, consolidation, and drain. Again, the drain has a difference of almost 50% from the undrained in this case. Next, modeling of the retaining wall as a plate or as a continuum. The blue line is a volume isotrophic element. The dash blue ones is plate isotrophic. The green one is volume anisotrophic, and the dash green is a plate anisotrophic. The plate element predicts a little larger than the volume, for the matter that when you model a volume, when you use a volume approach to model a wall, the shear side resistance at 2 sides tend to provide some form of a restoring moment. And if you look in terms of the percentage of relative differences of isotropic and isotrophic, you can see that again the drain is predicting larger displacement. This is obvious. And it's nice to see that the rest of the time-based analysis, a coupled analysis, falls within nicely between the undrained and the drain condition, which you have heard also from part 3 of the presentation. This is isotrophic versus anisotropy for horizontal wall displacements. This is the difference between a 2D and a 3D modeling for horizontal wall prediction. On the left is undrained, and on the right is drained. So the 2D is represented by the continuous lines, whereas the drain ones, isotrophic and anisotrophic, are represented by the dotted ones. 2D versus 3D modeling for horizontal wall displacements. Again, the continuous line represents the 2D prediction, in this case isotropic coupled analysis, and the dashed lines are the 3D analysis. Have a look at the relative difference in terms of percentage of 2D and 3D prediction. Next, bending moments, 2D again versus 3D. On the left are for the undrained analysis, isotrophic and anisotrophic, 2D, 3D, etc. On the right is the drain analysis for 3D ISO, 3D aniso, and 2D ISO. (2D versus 3D in terms of bending moments. Again, the continuous line represents the 2D analysis, and for the dotted ones, it represents the 3D analysis, ISO and aniso. Surface settlements, 2D versus 3D. At the top results represents the undrained analysis, and for the bottom is the drain analysis. And again, the 2D over predicts the surface settlement. (2D versus 3D modeling again. This is concerned with the surface settlements behind the diaphragm wall. The continuous line represents the 2D isotropic coupled analysis, and the two remaining dotted ones are for the 3D ISO and 3D aniso. Now have a look at the table located at the bottom. It shows the magnitude, and on the far right the relative difference in the analysis. The 2D, 3D isotrophic and the 2D, 3D anisotrophic. Summary: the influence of constitutive model on results of numerical analysis of deep excavation has been addressed. Simple constitutive models, especially elastic perfect plastic failure criteria, have severe limitations in predicting realistic displacements for deep excavations, in particular surface settlement behind a wall. Comparison with in situ measurement has been presented. Practical example of 3D analysis has also been presented. So for example 4, we will showcase the interoperability between Plexus and the structural, and in future the civil solutions in Bentley systems, to the use of ISM and the structural synchronizer. ISM, in short for Integrated Structural Model, is a workflow process that allows ISM-supported products to communicate with one another. The application you need for this workflow is the structural synchronizer. With the release of Update 3, Plexus 2D3 CE, the ISM now is a full-fledged tech. The previous releases, it was the tech preview. In this process, it involves creating a repository of a common data which is known as ISM repository from any ISM-enabled product. While you're creating repository, the structural synchronizer allows you to selectively save desired objects and properties into the ISM repository. Other ISM-enabled products can then import and make use of the ISM repository to bring selective objects and properties into their own interface. The interoperability is two-way, and at any time you can update the program with the new data. I'll be introducing in a simple fashion what is the ISM. In the later part of this presentation, engineer Sapat from our Australian office will be demonstrating these Plexus structural ISM workflow. The bigger picture, the use of ISM and structural synchronizer for data synchronization, change management, revision history, and model viewing is really enabled for many Bentley products. This includes analysis and design programs, structural as well as multidisciplinary BIM programs, and also competitor products. On the screen, you'll see that right now, Plexus programs are connected to the ISM repository. Now, ISM is a workflow that is available as tag in Plexus 3D. This is the final model that we will be building with the excavation pit. And I'm sure most of you know how to build this. It's not a very difficult excavation box to build. In the next few slides and video, Sapat will demonstrate these workflow. Over to you, Sapat.
This is a StatPro physical model example of a 10-story concrete building supported by a 2-meter thick raft. In the beam layout, we can see horizontal offsets that were automatically created using the axial end offset feature of the physical modeler. And this flushes the ends of the beams to the column surfaces. We have 2 lift cores in the middle and some shear walls to provide extra stiffness in resisting lateral loading along the slender direction. We begin the ISM workflow by first creating an ISM repository file from StatPro Physical Modeler. This launches the structural synchronizer, where we select and accept the objects and properties we wish to save into the ISM repository file. Here we are selecting all objects and properties, and then we hit the update button to finalize the repository creation. Now we can create a new Plaxis model of the building by utilizing the New from Repository option in Plaxis 3D. Here we select the same ISM file that was created earlier and begin the synchronization process. Again, we are selecting all objects and properties from the repository to bring into Plaxis. So this synchronization process of importing the building into Plaxis actually took around 10 minutes, but this video has been edited to save some time. And now we can see all the nodes, beams, and surfaces have been imported into the Plaxis model.
Now we have a marketing slide. This is the new licensing model from Bentley, and the sales consultant and engineers, you can contact them as per your respective regions. And this is Bentley geotechnical team for South India, Southeast Asia, and Australia and New Zealand. So if you have any queries, technical or related to sales, you can contact us.
Oh, very well. So with this, thank you, Rajendra Bish, logging in from our Mumbai office. So let's move on to the final poll question. Right after that, we will open up these webinar for some questionnaires. So I've seen the questions coming in from the Q&A, so I will answer one or two from it live. So Rajendra, can you push the poll question forward? You have 10 seconds. Okay, for those who finish, do know that all your questions, we have seen it, we have logged it, and our tech support and AE will be in contact with you for those questions that we can't answer it online or live. Now, there are one question that is of interest is this coming from company. It says that, do you have any idea on the modeling of water pumping in deep excavation in case of lowering groundwater table? Yes, this can be done. It's just that you need to know how to select this or create the hydraulic boundaries for it. So you can use sink. And when this is located at a point where it's similar to position of a pump, you need to then apply an outflow to create that pumping action. This is also good if you're doing this. It's best to run the full couple analysis, because if you run it in a steady state, you're looking at the time infinite here. The drawdown will be very extreme here. Now, the next question is someone coming from the user. The question is, do you need the PlexFlow license to model the transient condition? Yes, with the past 2-3 years where we have streamlined our calculation type, transient calculation option is attached to the full coupled flow deformation analysis. Yes, you need a PlexFlow license to operate the transient analysis. One more question. This is regarding more on how to get the parameters. It says that if you don't have enough data or laboratory testing, what happens if you use MC soil model? Is there any correlation of a deformation correction for this model? Well, let's begin with Mole Coulomb is not entirely a suitable model for the capture of deformation, whether it is a loaded problem or unloaded problem. My recommendation is that the HS model is the model that you start with, because the HS model is not a very difficult model to use. It's just that a lot of the users, they don't understand how you can obtain the stiffnesses, because the HS model do also use the Coulomb-Freeler criterion to capture collapse. And in comparison with just the linear elastic perfect plastic Mole Coulomb model, the HS model is a level up here. Now, if you don't have laboratory measurements, then you will have to then rely on field measurements. And field measurements perhaps depend on type of soil. Assuming there's a residue material, you have SPT, then SPT correlation, that you need to be sure that the collaboration works in that sense for your site. For deformation, you got to look at the problem, whether it is loaded or unloaded. For a lot of cases, this is for purely of a compression nature. The odometer test, which is in fact 1D compression test, very cheap to run. It's a good test to run instead of a triaxial test. So it's a good question. Perhaps if you're in doubt, always check with consultants and people in that sort of expertise to sort of provide you the kind of information here. So with this, Rajendra and I and Sapat, we thank you for your kind support. It's a slightly longer webinar because of the combination of the subject matter. And bear in mind that this is introductory, and please feel free to send us any emails if you have further questions here. So with this, we thank you for your support. Bye-bye.
Thank you.